Hi, this is Mr. West, and today we're doing a Kuta worksheet tutorial on independent and dependent events. What we're going to do is we're going to go ahead and start, and I'll talk you through what are the differences between independent and dependent events and how do we calculate the probabilities. So number one, you flip a coin and then roll a fair six-sided die. The coin lands heads up, and the die shows a 1. So is this independent or dependent? This is independent, and the reason why it's independent is because one of the outcomes does not impact the other in any way. If you flip a coin, it's going to be 50-50, heads or tails. If you roll a die, it's going to be either 1 through 6. But these two events do not impact each other. The die is going to be 1 through 6 no matter what, and the coin is going to be heads or tails, and they don't impact one way or the other if it's going to be tails or 1 through 6. So this is independent. Now, for number 2, a bag contains 8 red marbles and 4 blue marbles. You randomly pick a marble and then pick a second marble without returning the marbles to the bag. The first marble is red, the second marble is blue. I'm going to go ahead and kind of give you a demonstration of what this looks like. 2, 3, 4, and then there's 8 red marbles. So we're going to do this quick. 1, 2, 3, 4, 5, 6, 7, 8. Let's make this into a bag. Okay, so here's our bag. It's a wonderful bag, as you can tell. And we're going to take out one of the marbles. So we randomly pick a marble. It says the first marble is red. Okay, so if I go in, reach in there, sorry, trying to grab this. We take this out. There's the first marble. Now, just from me taking out the first red marble, you'll notice that the composition of inside this bag changes. Before, it was very likely that we're going to take out a red. Now that we've taken out a red, the proportion of red to blue has just shrunk. So now it's more likely that we're going to take a blue. So what does this mean? This means it is a dependent event. Because we remove some of the colors and we don't replace them, the composition changes, and so it's dependent upon the first event. The probability of the second event changes based on what we do to the first event. This is a dependent event, dependent probability. Okay, so I hope that was clear. We're going to do more, so if you haven't got it yet, we'll get it eventually. A box of chocolates contains 5 milk chocolates, 5 dark, 5 white. You randomly select and eat 3 chocolates. The first piece is milk, second is dark, third is white. So similar to the previous example, we have 5 milk chocolates, so go M, 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 M. 5 dark chocolates, D, 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 D. And 5 white chocolates, W, 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 W. Okay, so randomly select 3. The first piece is milk. So let's say we take out one of these, okay? It says the first piece is milk. Oops, I should probably put this one back. So the first one is milk. As I take out this milk chocolate, you'll see that it's less likely that the second one is going to be milk chocolate. Okay, so as I take out the dark chocolate, it's less likely that I'm going to get dark chocolate for the next one. So because the events of these two, or this one, or whatever order I'm going in, impacts the next draws, the next probabilities, these are dependent, okay? So if the probability depends on what happens before, it's dependent. Let's take a look at this last example. This is a good one because it talks about how it changes. Cooler contains 10 bottles of sports drink, 4 lemon, 3 orange, 3 fruit punch. 3 times you randomly grab a bottle, return the bottle to the cooler, and then mix up the bottles. The first time you get a lemon lime drink. So I'm guessing you're not even drinking, you just want to see what you get. So if we have all these bottles in there, okay, I'm not going to draw the letters this time, but we have all these different flavors. And if we grab one, let's see if I can grab it. Man, almost got it. I promise I'll get it in this time. There we go. So if I grab one, and then I say, oh, the first time I got lemon, and then I put it back, and then I mix them up, and then I go in again, and I grab another one, notice how it resets each time. Because it resets, the probability of the first one does not impact any of the second or third ones. This makes it independent. If it's reset, and the probability is the same each time without being impacted by previous events, then it is an independent event. Okay, now for the next part, 5 through 8, we are actually going to be calculating the probabilities. So let's go ahead and start with that. I'm going to change colors. So you flip a coin and then roll a fair six-sided die. The coin lands heads up, and the die shows an even number. Okay, so we need to think about the possible outcomes here. We have 2 possible outcomes with a coin. It's either heads or tails. So there's 2 possible outcomes, and the outcome that we desired is 1. Okay, a tail. What is it? Heads up. Now we have a 6-sided coin. So there's 1, 2, 3, 4, 5, 6. Which ones are even? Half of them. So that means that we have a 1 in 2 chance. Well, first let's say we have a 3 in 6 chance, which equals 1 out of 2. So we have a 1 in 2 chance for the coin, and we have a 1 in 2 chance for the dice of getting what we're looking for. What we do if we're trying to calculate the probability is we multiply these 2 probabilities together, and it's going to tell us what the probability of both these events happening is. When I multiply fractions, I do top times top, bottom times bottom, and I get 1 out of 4. If you want also, you could put this in decimal form on your calculator, and you're going to get 0.25. Both of these mean it's a 25% likelihood of happening. Okay, so we can figure out that percentage just from that. Done with that one. Moving on to number 6. You roll a fair 6-sided dice twice, okay? The first roll shows a 5, and the second roll, so this is number 1 first, and then the second roll shows a 6. So, probability that the first one is a 5, there's 6 numbers, as we showed here. Okay, I'm going to try to get rid of this. So if we have only one of those that we're looking for, the probability is 1 out of 6. And it's the same thing with the second one. It's 1 out of 6. So what we do is we multiply those 2 probabilities together, and we get 1 out of 36. That's the probability that we get. Now what I'm doing right now is I'm looking for my calculator. So we get a 1 out of 36 chance. So we get, let's go ahead and clear that 1 divided by 36. And we can type that into our calculator, and that is only a 0.0277 repeating. So we'll call that 2.8% likelihood of happening. All right. 7. There are 8 shirts in your closet, 4 blue, 4 green. You randomly select one to wear on Monday, and then a different one on Tuesday. This one's different. You might be inclined, okay, there's 4 blue, and there's out of 8 total. So our probability is just 1/2. You got to be careful here. For the first day, it is. Okay, for first day, we wore our shirt. We have a 1 in 2 chance of getting blue. But the second day, we used up a shirt. So now we have 7 total shirts. Okay, we're not going to wear a dirty shirt. And then we only have 3 blue left. So we have to multiply 1/2 times 3 out of 7. 8 total shirts, 4 are blue. We used up 1 blue. So on the second day, there's only 3 blue left, and there's only 7 shirts left. The probability that we're going to select blue goes down. 1/2 is bigger than 3 7ths. 3 7ths is the second day. Less likely that we're going to have a blue shirt. And we get 3 out of 21. Okay, and that's, oops, not 21. 3 out of 14. So then I type that into my calculator, just 3 divided by 14, and I get 0.214, which is about 21.4%. I could round that to 21% if I wanted to. That's my answer. Basket contains 5 apples, 7 peaches. Okay, so 5 apples, 7 peaches. You randomly select one piece of fruit and eat it. Then you randomly select another piece of fruit. Very similar to the previous problem. The first piece of fruit is an apple, and the second piece is a peach. So the first time we have 12 total. Okay, so the 12 total, and out of it we want an apple first. So this is our first pick of fruit. So 5 apples out of 12. Our second time we've eaten a fruit, so we no longer have that available. We have 11 left. And then we have to multiply how many we want a peach the second time. So now we have 7 out of 11. So the probability of peach is pretty good. And we multiply these 2 probabilities together, and we get 35 over 132. And we can just divide that, and we get 0.265, which is 26.5%. And there we go. That's our answer. All right, now down here, it's very similar to what you did above. It's that it just gives probability of event A, probability of event B, and probability of both those events happening together. Okay, so if they are independent, then if we multiply these two, this is the property of math that proves that events are independent. If we multiply events A and B, and it equals, so we multiply these two together, and it equals A and B, then we know it's independent. If it doesn't equal, then it's not independent. So what we're going to do here is we're just going to check. We're going to do probability of event A multiplied by event B and see what we get. We get 2 out of 25, and that's what it was here. So this means that these events are independent. Okay, it didn't impact it. They're completely independent, so the probability of them both happening is the probability equal to the probability that they happen together. Okay, so both happen one after the other is the same, so it's independent. They're not, it doesn't change depending on the first event, kind of like what we did here with the marble bag. Now, moving on to the second one. Same deal. So we have 2 over 5 times 1 over 4, and we're going to find out what that equals. Does it equal this? So 2 out of 20. We can reduce it 1 out of 10. So something's different. We got a different result, meaning that these two events are dependent, or maybe not dependent, but they're definitely not independent. Okay, so we can put not dependent for this. Something changes here. Or not independent, that's what I meant to write, sorry. Something changes here. There's not, most likely they're dependent. So one event affects the other one. So they're not independent. You could write dependent. We'll just do that for now. I think that's what the answer key says, but for now you can just write not independent or dependent. It's kind of the same thing. Either way, because they don't multiply together and give you the result of P and B, both of those events happen together, something is amiss. They're kind of like what we demonstrated here. One event affects the other one, okay? So it wasn't just that we multiply 4 out of 12 times 8 out of 12 because we removed it. We changed it each time we drew in the bag. This became 11, so it's dependent upon the first draw. That's probably the situation in this one. It's just harder to see because it's just numbers. This one's different. It doesn't say P and B. This one says the probability of A given the probability of B. So with independent events, if you're given that the probability given B happening, so probability of B happens first and then A, that's what this means, okay? So the probability that B happens first and then A happens, well, it shouldn't matter. If it's independent, this makes no impact. Let me erase this. We got a lot going on here. Having it given B makes no impact on that. So probability of A is going to happen no matter if B happens first or not. So if this and this are equal, then it's independent. Clearly they're not equal. So it's dependent. Something's amiss. Okay, so something happens where the probability of A changes with B happening first. That's what that means. B happens first. Okay, so that little slash there, B happens first, and this is the probability of A given B. So this is dependent, or you could write not independent. Either one of those. And the last one. So we have probability of not A. Got to be careful here. This is a trick. Probability of B, and then P and probability of P of A and B. So this says not A, and this one says probability of A. So what we have to do here is we have to find the complement. The complement means the opposite. So we know percentages of something not happening and happening need to add up to 100%. So if I have a probability that's going to rain tomorrow, that needs to add up to the probability that it's not going to rain. So let's say there's a 20% chance of rain. Well, if that's for rain, not rain needs to be 80%. Otherwise, something's wrong, right? It needs to add up to 100%. So if we have 3/4 here for, let me just move this down. So if we have 3/4 here for not A, then we need to add something to it where it's going to equal 4 out of 4. So obviously it's 1 out of 4. This is the probability of A. So probability of A is 1 out of 4. So we're going to do 1 out of 4 times, I changed it because I want it to be equal to this. 1 out of 4 times 3 out of 10, that needs to equal 3 out of 40, and it does. Okay, this is independent. That's what it means. Okay, so it's like the previous, which number? This is like number 9, but it tries to trick you with not A, but it's still independent because we can multiply probability of A times probability of B, and it's equal to probability of A and B. Okay, so that's the big idea that we are testing in these 4 problems. So that's all there is to this Kuta tutorial. I hope you enjoyed this video. Make sure to check out more of my videos, Algebra 2, Algebra 1, high school, middle school math, if you need help with any of those topics. Leave a comment if you have additional questions or you want me to cover something specific. And I look forward to seeing you next time right here on Wes Explains Best.